Let's get started. Let me firstly introduce our guest, Stephan. Stephan is an AI researcher who has been developing the AI economies, a multi-agent reinforcement learning framework for economies. Most recently, he led a research team at Salesforce Research. Previously, he also worked on imitation learning, model incorporation, and robustness in deep learning and multi-agent games. His research has been published in leading machine learning conferences and scientific journals, including Science Advances, and has led to multiple patents. It has also been widely covered in US and international media. For example, the Financial Times, MIT Tech Review, Forbes, Walkprint, podcast, and Dutch radio. He has served as an area chair for NeurIPS SAML. Before machine learning, Stephan studied math and theoretical physics at Woolwich University, Harvard University, and University of Cambridge, receiving a graduation prize for his thesis on exotic dualities in topological string theory. He then switched to machine learning research during his PhD at Caltech. He is originally from the Netherlands. Hi, Stephan. Please get started with your talk, AI economy.
All right, thank you, Zheng, and thanks everyone for being here, and thanks for giving me the opportunity to present my research to you today. So today I'll talk about the AI economist, which is a framework for economic modeling and decision-making using deep multi-agent reinforcement learning. And this research is the subject of the past 3 or 4 years or so. So the motivation for this research is that a lot of global macroeconomic challenges are caused by very complicated dynamics in the economy. And these are really big problems in society. So inequality in income and wealth is increasing. Global temperatures are increasing, and inflation is increasing, right? And these three problems are causing a lot of friction in the economy, and it's really affecting a lot of people in the world. But to actually understand how these issues are, how they arise and how we can solve them is actually really hard. So I think, the sound here is off. Can we?
It's an opportunity 1 year ago.
Oh, okay, let's not do this. It's probably bad. Okay, but I'll explain what's happening here. So this person is Jerome Powell. He's the chairman of the Federal Reserve in the US, right? So he's a very powerful economist because the Federal Reserve in the US sets the interest rate, which is the price of money, right, in America. And that's important because you can adjust that price of money to try to control inflation, right? So you can try to control how expensive things are in your economy. And what Jerome Powell is saying here is that, and this was recorded last year at a conference, he says that we now really understand how little they actually understand about what causes inflation, right? And so this is the most powerful economist, one of the most powerful economists in the US, who essentially is saying that, they can change the interest rate, they can look at what inflation, how high it is, but what happens in between, it's very hard to analyze. It's very hard to model, right? And so that's one reason that we have to look at new techniques to try to understand how the economy works. And AI is a very promising framework for that. So to introduce that problem a little bit better, I want to quickly talk about economics. And so at a very high level in economics, there's the micro level and the macro level view. So in a micro level, you can think about a marketplace where everyone goes to the grocery store or you go to the market and you buy some fruit, right? So there's an exchange of money for a good. And if you then look at the whole economy, then you have billions of people who are constantly making these transactions, making these exchanges of money for another good, right? Or goods for another goods and so on, right? And so a very important aspect of economics is the question is like, how can you understand this collection of billions of people who are generating even more transactions, right? Because the inflation part is, how expensive is a tomato in the market, right? That's what you measure with inflation, but it's influenced by all of these transactions that are happening by all the people in the economy. And so economics has like many unique scientific challenges. The first one is that there's no time machine, right? So it's very hard to ask counterfactual questions in the real economy. It's really hard to reproduce an experiment in economics. And the second is that if you look at the math and the computational models that people have of the consumer, like the agents in the economy, they're too simple. And so, for instance, like, like people have very complex psychology, people have emotions, but these models don't include those emotions typically, right? And then there are other examples where in models, for instance, people say, if you look at a marketplace, in the long run, supply always meets demand, right? But that's not always true. Sometimes people want too much, and there's toilet paper during COVID, right? In America, there was not enough toilet paper. So it's definitely not always true in the short term. There's a third reason is that there's too little data on how individual people respond to a change in policy or a change in prices. Like we don't track what people do on a day-to-day basis. And this really, again, it makes modeling behavior really hard. And fourth, the world is very diverse and heterogeneous, right? So what that means is that people's education level and income level are not the same. And if you try to put that into a mathematical model, it then becomes really hard to optimize analytically, right? So it's, and indeed, economics is actually often not really seen as a pure science for these reasons. It's more seen as a social science, right? Like, it's not like in physics where you can be in a laboratory and just, can reproduce the experiment and so on. So it's very hard, okay? Economics is very hard. And so why do you want to do AI in economics? Well, there are many reasons for that. And in this talk, sort of the mental model that you can have is that you can think of 4 areas in science. So there's analytic models. This is just equations and so on. Then you have data, and then you have simulations that you can run, and then you have machine learning, right? And AI is applied to economics is in the intersection. It combines these 4 domains, right? And tries to use that to provide a new framework to do economics research. So, so of all these things, probably a lot of people here know about machine learning, but maybe the simulation part is a bit new, right? So like I wanted to talk a little bit about what people have done in simulations. So what's the idea, right? So we have this picture of 1 billion people in the economy, and the question is like, can you simulate that using a computer? Now, this is not very like mainstream. Like, so today, if you ask an economist, how do you study an economy? People typically don't simulate 1 billion people in a computer, right? But some people have tried to do at least a part of this. And so one of the first attempts was in 1970 or around, in the 1970s. And this is like some early work done by Jay Forrester. So that's this guy in the bottom right. So Jay Forrester was this pioneer at MIT, and he had access to one of the earliest mainframes, right, at MIT at the time, and he was really interested in economics, and he said, okay, let me just try to make this simulation, and like you can see in this flow diagram that he really tried to model a lot of parts of the economy, right? So he had people in there, he had money in there, he had real estate, he had companies, he had the government. So you can look at this diagram, right? And this diagram it's very complicated. There are like a lot of boxes, looks kind of like a circuit, like like a computer. And Jay Forrester really thought about the economy like a computer system, right? Like you had all these components, and then he had like, if you can actually read the book, and like if you look at the book, he has like 100 or 200 pages of rules. And he says that for instance, if the price of tomatoes goes up, then that effect is then fed it to other parts in the circuit, right? And then like there's some rules about, if the price of tomatoes goes up, then people are going to buy fewer tomatoes, right? And then like, maybe like the company, the tomato producer, the farmer has to produce less, and so on and so on. It's very complicated.
This system is deterministic.
Deterministic, yeah, I think it's mostly deterministic. So the keyword here is that there's a system, right? Like you have this deterministic set of equations and some initial state, and then you just look at what happens in the system. Yeah. And again, this is 1970. Okay, this is like very, in a way, it's very primitive, but Jay Forster had this idea, right? This vision that we should build this sort of digital twin of the economy. Then what's interesting here is that some people took this serious, right? And so what I showed you was called World 1, there was World 2, that was the name of this simulation, and then there was World 3. And World 3 led to this study that was called the Limits to Growth. It's very interesting. So there was this organization called the Club of Rome, okay, and the Club of Rome was a group of famous economists, famous politicians who got together and said, we're important and we should think about the future of Earth and the future of the economy. And so they said, we're going to use one of these simulations to look at what's going to happen 100 years from now. Okay, again, this is 1970s. Okay, this is like, they had like, pretty slow computers, and then they said, what happens, for instance, to how much food per person in the world, or how much industrial output per person, right, do we have, and what happens to the population? And like one of the interesting things here, right, is that they said, well, you can also look at pollution. They were pretty ambitious, right? And they said, like, the important thing here is that the red line and the black line, they said, if you look at the number of resources in the world, like how much oil, how much gas is in the world, there's a limited amount, right? Like at some point we're going to run out of oil, okay? And then, there's all kinds of other effects that happen in the simulation, but the effect is that the world population is going to actually hit a peak, right? And then it's going to decline again, right? The world's going to shrink. And so this Club of Rome said that we're going to challenge this very classic economic concept that the economy should always grow, meaning we should make more money, right? We should, get more resources. We should make more iPhones. We should, make more cars, right? Like it cannot continue forever. That was sort of the message of the Club of Rome. Now, this is controversial, because you can imagine that this is a projection 100 years into the future based on some computer simulation. That is obviously a bit of a toy model in a way, right? And so this got a lot of criticism, but it gives you a sense that some people were thinking really big, like when it came to economics and computation. Now, I said that like one of the limitations of these models is that the consumer, the agent in this model is very simple, right? And in particular, in that flow diagram, there's not a billion people in the computer simulation. And so after that, like, some other sort of follow-up work was studying something called agent-based modeling. So in 1996 and 1989, there were a number of computer scientists and economists and physicists who started to write these computational simulations where now they really try to have a billion individual agents in the economy, right? So in the 1970s, you had like, one equation for the consumer. Now in these simulations, people said, well, what if we really had a billion little individual consumers, right? Like then, can we say something interesting about the world? Like you get these programs, this looks very primitive, and it is still very primitive. But the point here is that they really try to get at these 1 billion individuals, right? And then get at the complexity, right? So this is still very primitive in a way, right? Because in this agent-based modeling exercise, the behavior of these agents is still based on rules. Okay, so there's still a very simple if-else rule that determines the behavior. So it's not very smart. Okay. So now we get to around 2020, right? So 2023. So what I want to talk about is the multi-agent reinforcement learning view in economics. And essentially what one of the ways to think about it is that instead of having like these rules for the behavior of all the agents, now we're going to use reinforcement learning agents, right? And so in this picture, we're going to have a simulation again. So that's like this cartoon in the middle in the blue box. And then every agent in here, like the people, the government, the companies, they're going to have a neural network that's going to learn what the optimal behavior is of those agents in the economy, right? And in the best case, you will have 1 billion neural networks, okay? 1 billion people, billion neural networks. And then we're going to do reinforcement learning. And then we're going to train every neural network for some given objective. And this is like the pretty standard reinforcement learning objective. And then, you can use real data and all kinds of priors about the world to look at some of the structural parameters in a simulation. And then the idea is that once you have that simulation and you have these agent models that are hopefully very realistic, right? Then you can use that to ask questions about the economy. Like, if the prices change of tomatoes, then how does the behavior of people change, right? And then how does that then change inflation? And then the hope is that this gives you a better understanding of how the economy works. Now, the name of the seminar is like trustworthy machine learning, right? And one of the things here, what's interesting, and this is also part of what my research was on, is that so the people, are modeled by neural networks, but you can also have neural networks that model companies and the government, right? And that means that you can actually try to design government policy using neural networks, right? Because the government has to optimize, do this very complicated optimization problem. And then the question is like, why would anyone trust, a neural network to set government policy? So there's two things that are really important. So one is explainability and interpretability of these models, right? So if you talk to economists and you say, I have a good model or a better model of economics, then they will say, okay, why? Like, how does it work? How does the world actually work? And you need to be able to explain why does the neural network, decide to increase taxes or decrease taxes? Why is that? Like, what kind of features in the simulation cause the neural network to make that recommendation for you, right? And the second one that's really important is that this question of value alignment. So for instance, if you have this government neural network, you can ask it to optimize for economic growth, right? But the question then is that the right objective, right? Like, should we also care about inequality, or should we care about, the climate, and climate change, right? And so there's this discussion, like, what is the right reward function, right? And so that is again like a very important design choice, right? That this has nothing, well, it has something to do with machine learning, but it has a lot more to do with society, right? Like, Japan is a democracy, right? Not every country is a democracy, but so the question is like, what kind of reward functions would you give to the system? And then that's a very interesting sort of connection between machine learning and social science. Okay, so that was a long introduction, right? And so the question is like, okay, if you take this framework seriously, you can ask, well, what will be the ImageNet or ChatGPT moment for AI and economics, right? Meaning, when will this framework be the standard framework for doing economics? So why would we use this? Well, if you use neural networks, you can perhaps get better models of the behavior of people and companies and the government that might in turn give you better macro predictions, right? And so there's many research results in recent years that showed that things like imitation learning and reinforcement learning can both model human-like agents and also optimize better than the existing tools that economists have, at least. And then this might be preaching to the choir, right? But what's interesting is that a lot of the advances in recent years in machine learning have really been enabled by just bigger models, just bigger neural networks, bigger data sets, bigger computers, basically. And then the interesting question here is you could also build bigger simulations, right? And then in turn use bigger simulations to train more realistic neural network models of behavior. And so like that scale is another reason why now might be a good time to go to the next level in economic modeling and convince people that that's actually a more powerful way to model the economy. So very high level, the question is, like, when will AI be the standard framework for economics? And so there's, you need to do more science. There's definitely a lot of algorithms that we need to develop further to solve economic problems with AI. But we also have to do a lot of engineering. So, build software frameworks to build big simulations, to run them on GPUs, to, run them in distributed computing environments. We need a community, like, where people build benchmarks, where they build data sets and look at different economic scenarios, and also perhaps a compelling application that a lot of people care about. So for the rest of the presentation, I want to talk a little bit about my recent research and some projects that touch on all these four aspects to hopefully give you an impression of the work that I've been doing with a bunch of other people in this space. So maybe it's a good time to pause here and say that, if you guys have any questions, just interrupt me and I can pause.
So I have questions.
Yeah.
Is there really have such a simulation you stated? It's already developed, the simulation multi-agent reinforcement memory for the simulation of the
Yeah. So I'll show you one for income taxes that we built.
I see.
Yeah, and there's an open source framework that we built with the AI economist that you can use to build more simulations. And right now this is private still, but we are working on some really big economic simulations that are used by the US government, actually. So something on that scale.
I see.
Yeah.
That's nice. Yeah, and another question is kind of like evaluation.
Yeah.
Who can evaluate this? How to evaluate this?
Yeah, so if you're an academic, you can just compare the baselines, right? So the baselines are economic theory.
Exactly.
But in the real world, you ultimately want to deploy these policies and see if they actually work, right? And so that is hard, right? Because you
have some risk.
Yeah. And so that I think that is long-term what you want to do, but we're not there yet. Yeah.
Okay. Hi, audience from remotely. Do you have any questions? Please feel free to ask. Maybe we can proceed and we can ask.
Yeah, sure. I just want to say that, if you guys have any questions, just feel free to chat and we can answer them. Okay, so the first project I want to show you is about designing tax policies using this framework. So this is the first project I did when I started thinking about this area. So I apologize for the simple simulation. This is really what I could do in using Python and some other stuff. But the challenge here is how do you design income taxes? Okay, and so going back to this framework that I showed you before, we have the simulation of the two-dimensional world, and in this world, agents can collect resources like stone and wood, right? And so these agents are working to collect these resources, and then they can build houses with them. And once you build a house, you earn some money. Okay, and then these workers also pay taxes. So there's also a government in this world, right? And this government is deciding what the tax rates are, right? And so, the government and the workers are all, again, controlled by these neural networks. But the special feature here is that this yellow neural network is the government, right? And when the government changes the tax rates, it is actually affecting the the reinforcement learning problem for the workers, right? So in more sort of jargon, this is a mechanism design problem with adaptive agents. Right? The mechanism is the set of taxes that influence the reward function for the RL agents. So what you do is okay, well, you have a bunch of neural networks. So the structure of the neural networks is not super revolutionary, right? But there's two types of neural networks. So one is for the planner. So that's the government. So planner is it's a word from economics. So all these, so you train a recurrent neural network it looks at all the information of the world. So things like, there's a market in the simulation. So people can sell these resources to each other. The government can see what the prices are. It can also see how much money these agents have, so what is their endowment. And then the government then uses the neural network to set the percentages of income tax. And so, yeah, I'll show you later how that works. But the idea is that there are like 7 percentages. And so that means, for instance, like if I make money, then the first $1,000, I have to give 20% to the government, right? Or 25% to the government. Now, the agents have a similar recurrent neural net, right? But then the agents decide, oh, in this world, where am I going to go? Or I want to build a house, or I want to sell my resources or buy more resources. And yeah, these neural networks also use a similar set of information. And what's important here is that there's like private information and there's public information. So for instance, like there is like a skill level between these agents, meaning like the quality of the houses they build is not the same, right? And this is something that only the agents can see. And the government cannot see how good you are at your job, so to say. So they're like, there's like these little design choices in the simulation that are that follow the classic economic framework, right? Okay, so so now we have these neural networks, right? We have the simulation, and now the what is like the optimization problem here? Like, why is this a hard problem? Well, as I said before, as you are making money, you're paying taxes on them, and then the reward function changes because basically the more money you make, the happier you are. Okay, but if you pay more taxes, then that makes you less happy, right? So every time the government is changing its policy, and if you update the model of the planner, right, then the distribution of taxes that these agents are going to experience is going to change. And so you get this bi-level optimization problem, right? And so every time the tax is changed, the taxpayers will need to relearn what the optimal strategy is for the given set of taxes, right? And so if you look at the economic theory, there's really no explicit solutions. It's a very hard bi-level optimization problem. It's sequential, it's dynamic. There's like no closed form analytical solution for this, right? So here are the objectives to make this a bit more concrete. So in the top line, you see the objective for the planner. So there's a social welfare function, and like the instantaneous reward is the gain in the social welfare for the planner. So like you just look at every time step if the economic growth went up or down, for instance. And then for the agents, the reward is the gain in utility. And so the utility function U here is this combination of consumption. So that's this capital C, and then consumption. There's like a power law here. So 1 minus 8 is just like some fixed exponent. And then the idea is that the more money you make, the more you can consume. So the bigger C is. So then you get positive utility, but then you have to subtract the labor that you have to do. So like the more you work, the less happy you are, right? And then the other thing is that this C here, we also have to subtract the taxes from that. So it's like the post-tax income, right? And then you can see that as the planner is changing the taxes, this utility function is going to change, and that changes the reinforcement learning problem for the workers. So when you look at your sort of performance plot, so this is like a very typical picture, right? So here, like in green, you can see what happens if you have this reinforcement learning algorithm, train all these agents, right? So again, bi-level optimization. So the government and the workers are both using reinforcement learning. And what you see is that the objective here, the vertically, is the planner's objective, the social welfare function. And in this paper, we actually chose this product of equality and productivity, right? So the government wants to have a lot of money that is made in society, but it also cares about income equality. So people should hopefully make a similar amount of money. And then you can see that the objective actually doesn't go up monotonically, right? It goes up and it goes down, and it goes back up again in a green case. But in the end, like that green line does give you higher social welfare than all the baselines. Now, why does this green line go up and down? That's because of this, like, this bi-level optimization issue, right? So in the green line, you can see that the planner initially finds some tax policy that increases social welfare. But then because the workers also use reinforcement learning, they will find some way to actually pay less taxes, so to say, right? And so then like the objective goes down again, and then the government has to again adapt, right? So you get this sort of back and forth. And so this picture is only if you do a bunch of like learning tricks, right, to stabilize learning. If you don't do that, then very often like learning just completely fails, right? So this is actually a really hard optimization problem. Okay, so how do you stabilize this? So this is just like in words, like a bunch of tricks that you can do. So you can train everyone using PPO, but then you train in phases. So what happens in our learning setup is that we actually first only train the workers and the taxpayers, and we keep the taxes fixed, okay? So we then basically let the taxpayers learn what they should do under different tax policies, but the tax policies use this fixed distribution over time, right? And then after a while, you then start to train a government, right? Then the government says, okay, now I can use my RL policy to train. And this sort of the structured curriculum actually stabilizes learning a lot. And the second thing is that once you start to train a government, you should also slowly increase the action space. So like, you don't let the government change set the taxes at every possible percentage, but you first have this small range of 0 to 10%, then 0 to 20%. And so like the distribution of taxes that these agents are going to see, it changes very slowly. So like that's also like it's sort of a curriculum that you're introducing, right? And so we found that this is very, very effective. So what you then see is that empirically, right, is that you can stabilize this green curve, and then you will converge to something that is better than all the baselines, right? Now, what's important here is that the important thing here for us was just beat the baselines, okay? In machine learning, we just beat the baselines. We're happy, but there's no guarantee that that is in fact a global optimal solution, or that it's like the game theory equilibrium, right? Okay, so in plots here, okay. So what's the final result? So when you do this curriculum learning and all the tricks that I just mentioned, when you stabilize this two-level reinforcement learning procedure, then you do get higher social welfare, right? So you get 60% higher equality times productivity in the economy. And then you can see that all these baselines here have lower social welfare. But in particular, you can see that like what's interesting is that if you look at the productivity and the equality separately, you see that this AI solution is not the most productive, right? But it is the most equal in income. And it's this combination that is like actually better than all the other baselines. Now, what are these other baselines? So the first one is the free market. In the free market, there's no taxes, okay? No taxes, nothing. In the second, it's the taxes that are used in the US, more or less. That means that as you make more money, you pay higher tax rates on that higher income. And then the third one is the so-called SAS formula. So the SAS formula is like this theoretical solution. And in this case, it actually leads to regressive taxes, meaning that as you make more money, you actually pay lower tax rates, okay? So it's interesting, right? You have progressive rates, regressive rates. And now what is really important here is, so let me actually go to this slide here. I mentioned, right, like you have progressive rates, that's what's used in the US. Then you have the SAS formula, which gives you regressive rates. But then the tax rates that the AI solution finds are actually like weird. It's like a hybrid, right? So what you see here on the right, let's look at this like A plot. So it might be a bit hard to see, but if you look at the brown lines, that's the US federal taxes. So you can see that as you make more income, the tax rates go up. For the SAS formula in yellow, if you stare at it a little bit, you'll see that as you make more income, you pay less taxes, right? Like this yellow line here on the right, like are lower. But then the AI solution is in light blue. And like, strangely enough, the light blue lines go up and down and then up again, right? So you have high tax rates in the bottom, low tax rates in the middle, and then high tax rates again at the end, okay? So very strange, like, it's not something that most economists would come up with. And so that's one of the main messages, right? Like these kind of hybrid policies actually give you higher social welfare, but they might not be the simplest to explain, right? And this is hard.
I have a question.
Yeah.
For the time frame.
Yeah.
So to project it to the real world,
Yeah.
what kind of time frame do you think? Is it 100 years or maybe 10 years?
Oh, yeah. So this is 10 years roughly.
10 years.
Yeah. So in the simulation, there's 10 times where these agents pay taxes. So then if you think about it,
Every year.
you pay taxes.
I see.
Yes.
Thanks.
Yeah. Okay. So the first conclusion here is that the AI policy is not the same as what classic economics predicts, right? But it does do better. Okay. And the second thing is that in the simulation, what's interesting is that there are like some, even though the simulation looks very simple, there are some features of the real economy that are emergent in these simulations, right? So the first thing is that these agents are learning to specialize. So what that means is that like this orange guy in the middle builds a lot of houses, right? But the other agents now, they don't build as many houses, but they just stick around the areas with the resources. So that means that some agents learn that it's actually better for them to just like gather these resources and sell them to the orange agent. And the orange agent doesn't actually need to gather as much, but he should just like start building houses, and he can use the profit from those houses to actually buy more resources, right? So that's kind of interesting. The second thing is that these agents then actually learn to game taxes. Like that means that this is a dynamic system, right? Like there's 10 years where these agents pay taxes. And what we see is that these agents are actually starting to learn strategies to minimize how much tax they pay. And this is like kind of like this tax gaming that happens in the real world too, right? So that's kind of interesting, right? And so why is this cool? Well, this gives you again a flavor of the idea that these economic simulations in the future could actually be like the real world, okay, right? And like the ultimate goal is to build a simulation of the economy that reflects how the economy really works, right? And so even in these very simple simulations, you can see that some of these features of the real economy are emergent, right? And so that's why, like, if you make these simulations bigger, you can hope that at some point they're going to approximate the real economy. Okay, so this is really cool. We're not the only. So after we wrote this paper, our paper was published in Science Advances like about a year ago, and then our friendly colleagues at DeepMind said, "Oh, this is very cool," and so they came out with this other work that came out after us, and this work appeared in Nature Human Behavior, and it's something called democratic AI. And so actually in 2020, when our team first published this paper, or put it in the archive, I should say, we actually had this little experiment, but we actually put real people in a simulation, and we paid real money to people and asked them, build houses. And every time you build a house, you actually get $1, okay, or you get $2 or 50 cents, right? And then, but it actually didn't make it into the Science Advances paper. But then DeepMind said, let's focus on this human aspect, right? And so what they did is they said, okay, let's make a game, right? And now there's like 4 people, real people, okay, who are going to play this game. And what happens is that everyone has some money, okay, and then you can choose to put this money into a public investment fund. Okay, and then after a while, this investment fund will have some profit, okay, and this profit has to be redistributed. It has to be given back in some way to the people who put the money initially into this fund. Now, there's different ways in which you can think about redistribution, right? You can give everyone the same amount, okay, that's completely socialist, you can just give them the return proportional to their original investment, right? Which seems fair, right? And then you can do things that are in between. And the question is, what's the best way to do this, right? Again, same question, like we have some social welfare function. The government has to choose how to redistribute and what happens, right? And so in the middle, you can see this plot. It's a bit abstract, but the idea here is that you can say, on the one end, there's this extreme socialist view. On the other hand, there's this extreme sort of individualistic view. And somewhere in the middle, there's some hybrid where like you're going to share a little bit. So, maybe the person that put in a lot of money, let's say 80% of the fund, doesn't actually get 80% of the profit. Maybe they only get half, 50%. And then so there's a little bit of like sort of more equality after we redistribute the profits. Okay, so and so in this project, DeepMind said, okay, let's use reinforcement learning to learn how to redistribute. Okay, and what we need again is a simulation. So they use some combination of imitation learning on human data to build a simulation. Then do the same sort of idea that we did with the income taxes. So use a simulation, do this 2-level RL, and then they find this reinforcement learning redistribution policy, which is like this thing here in purple. Okay, and just imagine it's some hybrid again. It's like not purely socialist, it's not purely individualistic. It's somewhere in the middle. But it turns out what they showed is that real people actually prefer the AI policy, right? So the same conclusion as our work, right? So we get this hybrid AI policy. It gives you higher social welfare, right? But it's not like what the classic theory or would predict, right? They found the same thing, and they found that real people actually prefer it. So this still has these issues, right? Like it's still a neural network. It's hard to explain perhaps, right? Like, at a very low level, why it's such a hybrid, but you can see it's a hybrid sort of these classic theories. But it turns out real people prefer it, which is really profound. So the question then is, would this also be true in the future, right? So if in tax policy in the future, in the real world, is designed by AI, is that at some point preferred by people? I don't know the answer, but this is like some early results that indicate that in very simple scenarios, real people actually prefer what the AI does instead of what human politicians come up with. Okay, so some other projects here is this. So I'll sort of quickly go through some of these other ones. So here's an intern of mine, Michael Curry, who basically built a simulation where you also have companies. So you have a planner or government, you have workers, people who pay taxes. Let's not add up companies too, right? And so now the idea here is that the simulation is more complicated. Again, we're going towards this world one, like of Jay Forrester. You have more components, more relationships, more interactions. And essentially what Michael showed is that now you have not a bi-level, but it's like a hierarchical reinforcement learning optimization problem, right? And every arrow here, again, is this sort of internal mechanism design problem, right? So, if the government changes taxes, it's going to change the optimization problem for the consumers, but it's also going to change the optimization for the companies. Every time the companies change their prices or the wages that they're paying to the employees, they're changing the reinforcement learning problem for the employees. So again, this is an extremely hard hierarchical reinforcement learning problem. And Michael showed that if you have this, again, you use these structured curricula approaches, then again, you'll have the same conclusion. Like the AI policies will do better, will give you higher social welfare and so on. And so this is like an AMAS this year, actually, in London. I have to update this slide, but it's going to appear in AMAS. Then this was a project that I did with another intern, Tang Mu. And so she worked on this project with more realistic agent models, where essentially we wanted to bring behavioral economics into these simulations. So what this means is that in economics, there has been some research on how you can have things like emotions in these agent models. So I mentioned that most economists don't use behavioral models because it's really hard to optimize for them analytically, right? But now, because we've reinforcement learning, we can combine some of these behavioral economics models with our reinforcement learning framework, right? And so you can ask questions like, what if you only have a limited amount of energy and time to attend to different information in the world, right? So there's a cost of attention, essentially, and acquisition of information. How does it change the behavior of people? And so she looked at the situation where, like, you have a so-called principal agent problem. So the principal here is like a manager, and the agents are its employees, right? And this is a very classic problem in economics, okay? Principal agent problem. And the problem here is that the principal, the manager, doesn't have all the information that's private to the agents, like, again, the skill level. The principal doesn't really know how good you are at your job, okay? But in order for the manager to figure out if you're actually good or bad at your job, it actually needs to spend some time, needs to spend some money, right? And it's not easy. And what Tong found is that, maybe what you might expect to some degree is that as the cost of information acquisition about the skill level of these agents goes up, sometimes the principal should just like pay more money to everyone because the team as a whole will do better. Why? Because like some people are actually really good at their job. If you pay them more, they will work harder. So the team will do better. But then the problem is that there might be some employees that are not so good, right? And those bad employees will actually be like free riders, right? They get paid more, but they didn't really do a good job. But sometimes it's actually better for the principal because the net result is in fact more profitable, right? And so the interesting thing about this paper is that you can now basically start to look at these more complicated principal agent problems using reinforcement learning. So this paper appeared in like the Transactions of ML a while ago. Okay, so I do have one project with like a little bit more detail I want to go through. So there are like two papers where we also looked at some more algorithmic, sort of innovation. So the first one is about robustness. So, how can you make robust mechanisms? And in particular, how can you be robust when at test time, the agent models have a different policy, right? So for instance, you can basically train in your simulation with agents that are purely rational, right? Using that utility function I showed you before, or you can and then you can test on agents that have some behavioral economics in them, right? They have some, some limitations to them. So then like your simulation at test time is going to be different, but you still want your government policy to be, robust to that, right? And so in this paper, essentially, we showed that there's a way to do some form of meta adversarial training, basically, where at training, you have to sample adversarial agent policies, right, to make your government planner more robust, right? And this is hard because like now you're not talking about, like in adversarial robustness for images, like you have a gradient, right? Like you just adapt the image itself. But now you have to actually adapt the policy model of the RL agent, right? So now, you have to do a little bit more complicated things to make that work well. Okay, so then the second paper that this is very recent, and I want to go in a little bit more detail on this one, is something called Mermaid. And so Mermaid is this question again of like, how can you like learn a mechanism that does very well when the agent itself is still learning? So the title is like aligning learning using model-based meta learning. So the idea is like a bit more simple, more stylistic. So again, we have a planner, a government, and a learning agent. And let's think about like some pretty simple binary choice, right? So you can buy a car, okay, and then you can buy a gas car. That's the red one, which is very dirty, there's a lot of pollution. Or you can buy a hybrid car or electric car, right? That's the one in blue, right? And so the idea is that, imagine there's this case where, you have a consumer and, they can choose to buy either car, but maybe the gas car is just really cheap, right? And then so the consumer by default wants to buy the dirty gas car, okay? And then the government wants to incentivize this consumer to instead buy the electric car, right? And so you can imagine that maybe the government has some subsidy for this. And this is actually what happens in the US, right? The government has all kinds of tax breaks, and you pay less tax if you buy a cleaner car, right? Now, the algorithmic problem here is that as the consumer is optimizing its policy for its reward function, right? Now, the government can try to intervene on this learning process, right? And the question is like, how can you learn this intervention policy, and again, in such a way that you will generalize well to agents that you haven't really seen before, okay? So, and this is really important, right? How do you do this generalization to test time agents with the learning algorithm that you haven't seen before in a very robust way? Now, so that's hard, right? By itself. But what's important here is that, like, you know, these interventions here are costly. So the government can't just like arbitrarily add reward, okay? Because that would be silly. That makes the problem trivial, right? Because like if the government could just sort of subsidize infinitely, they could just make the electric car for free, right? And you know, of course, everyone would choose the free option. Okay, so the second one is that we're considering costly interventions, right? And then the third complication is that there's partial information. Like the planner doesn't really know everything about the agent's algorithm that is using to learn, nor the rewards that it's actually receiving, right? So, you know, because like again, like the economic concept here is that the reward function that the agent sees is its utility, right? But the utility is something that's like internal in our brain, right? Like I can't really see like how happy you are. I can maybe only ask you to do so, right? So here's like the sort of formal setup. So the planner has this this optimization objective. It has some reward function, and you can think of this reward function as I get a reward of 1 if the consumer buys the electric car, and 0 if they buy the gas car. Okay, and I have to subtract the cost of intervention here at every time step. And what I want to do is that when I sample a consumer with a learning algorithm for the test set, I want to do very well. And then the consumer here, you know, basically experiences this intervened reward, right? And this is conditional on the policy of the planner. Okay, so in this paper, Mermaid, basically, yeah, as the title suggests, like we're using this combination of model-based learning and meta-learning, where basically like you have two things. So you use a world model to mimic the behavior or to learn the behavior of the agent as it's learning. And then that feeds into this intervention policy that sets the that decides when the government intervenes on this reward, right? Now, the other thing that's important then is that there's this modeling part to it, but then you can also use meta learning on the planner, right? And so you have to adjust the meta learning procedure here to actually collect samples for the meta learning update. So the idea is that because of time, maybe I can't go through the entire algorithm box, but the idea is that in the meta learning setup, like you have a bunch of different tasks, which are like agents with different learning algorithms or different learning hyperparameters. And then during training, you're going to learn a planner policy for each of these different agents. And then based on all these individual planner solutions, you can then also learn a meta set of weights, right? And then update that one using meta learning, and then that gives you a some sort of meta planner policy, right? And it turns out that gives you a very robust initialization at test time to then do very well on test time agents. And so here's like a table of the results. So what happens here is that there's essentially two learning algorithms for the agents. So you can use UCB agents or epsilon greedy agents. So these are fairly standard banded algorithms. And then you can have different exploitation rates for UCB, different epsilon for the random accent selection epsilon greedy agent. And what you do is that, in the top column, in the top row here, for instance, you train the planner on UCB agents with beta equals 0.17. And then at test time, you give it agents that have a different beta, different exploitation parameter. And then you see that if you use the mermaid approach, it does better than all the ablations basically where you don't use meta learning or you don't use a world model. And then like all of these components are really important for you to do very well. And then importantly, like what you see is that both in the 1-shot and the 0-shot setting, Mermaid actually does better. So this, this combination really is pretty powerful. And you can do the same thing for epsilon greedy. So you train on epsilon greedy and test on epsilon greedy, but you can also do the other thing where you train on UCB and then you test on, sorry, like, am I saying that right? Let me see if that's here. Yeah, so, sorry, this is like, the third one is still UCB, train on UCB, test on UCB, but with different hyperparameters. And then here's what happens if you train on UCB, but you test on epsilon greedy agents, right? So this is really like, really the test time distribution is really different, right? And then, you can do the same thing, epsilon greedy, train on epsilon greedy, test on UCB. And again, you see that Mermaid does better, okay? So that's pretty cool. Now, intuitively, what's interestingly here is that sometimes actually Mermaid does not do better. Now, why is that? Well, it has something to do with the exploitation behavior for these agents. So the idea here is that if you train on bandit agents that explore a lot, right, then you have more opportunity as a planner to intervene successfully and change the learning outcome for the agent. So if you look at this, if you look at the results here, you can see that for beta equals 0.42, when you basically have good exploration, and then at testing time, these agents are how should I say this? Have a small epsilon. So then basically you can generalize better, basically, because you've trained on something that explored a lot, and at test time, the agent is exploiting a lot. So basically, like, they will very quickly adapt to your intervention that you've learned, right? Whereas, like, if the agent at test time is exploring a lot, then it's harder for them to cache onto your intervention, right? So that's intuitive. But the reverse is also true. Basically, if you train on, and so I think that results actually, well, not in here, actually, I say I don't have that here. But okay, but in words, basically, the idea is that if you basically train on an agent that does not explore a lot, then interventions are not that effective, so to say, and then you will generalize not so well, if that makes sense. I apologize that that table's not here. Anyway, so there's this intuition that, like, the behavior, the high-level behavior of these learning algorithms for the agents influence how well the planner can generalize and how effective Mermaid is going to be. Okay, so how long do I have? Are we almost done, or how much more time do I have?
How long do you need?
I have one more project I want to talk about briefly, but I can have maybe 10 minutes.
Yes.
Yeah? Okay. Okay. Yeah, I'm not sure how long this usually is. I feel like I'm talking a little bit too much. Okay, so I gave you a bunch of science projects, right? And, like, I mean, I hope to convince you that there's both, like, economic modeling here combined with some algorithmic innovation, right, to make multi-agent RL work better for these types of economics problems, right? But there's also engineering challenges. So the other project we've been working on is something called Warp Drive. And the idea of Warp Drive is that you can run the simulation and the neural network agents on a GPU, right? Because very often people have simulations that are running on CPU, right? And so if you actually put everything on a GPU, then you eliminate all the communication overhead, basically, and it makes training way, way faster. So yeah, like, if you use Warp Drive, essentially, you can get these speed ups where, for instance, like, it depends on the simulation, of course, but, in one case here, you get a 24 times faster end-to-end multi-agent RL, okay, if you do this approach. And you can get even faster speed ups, really depends on your simulation. And so what's cool about this is that the latest version has support for Numba, so you can basically write your simulation in NumPy, and then you just, like, do drop-in replacement with Numba. It will be on a GPU, and then things will be very fast. So yeah, if you're ever interested in making fast simulations, and check out WarpDrive. Okay, so the last 10 minutes, I want to talk about this project that's going on right now. And basically, this is like talking a little bit of the last part, where we want to have this community of people that are working on this big problem that a lot of people are very interested in, and that hopefully is a catalyst for sharing research and sort of this like group project around building simulations and doing experiments in this AI and economics space. And so what we came up with like a while ago is AI for global climate cooperation. And so this is a project I'm organizing together with some people from Mila and Lou. She's at UPenn. So at Mila, we have Yosha Benjo and a bunch of the students. And the challenge here is to design a climate negotiation game to incentivize cooperation, right? And to optimize climate policies for a set of outcomes that we want to achieve. And so we set up this competition, we built a simulation, we calibrated to real world data, and anyone can participate. You can implement your own negotiation protocol and then use the whole machinery that I described so far to convince people that your negotiation game is realistic and is something that we should really use in the real world. Okay. Now, this is a bit like sort of timely because, like, maybe you guys have seen this result that Noam Brown basically, sort of worked on with his team at Facebook, which is this like Cicero bot, right? And so in Cicero, it's like this AI bot that beat people in diplomacy, which is like this negotiation game where every agent is controlling this country, and these countries are at war, right? And then you have to negotiate because you can't really win the game on your own. Okay. And so one way to think about this competition is that we're asking the inverse question, right? We're saying, what is the right game, right, that actually incentivizes these countries to work together on climate change? Like, can you design that game? Can you design the rules of the negotiations and then show you that the optimal behavior in this game is cooperation? And so why is this so timely, right? Like, climate change is important, right? The world's getting warmer or colder or more extreme. And if you look at the report from the IPCC from last year, they actually focused a little bit on this question, like, what is the impact of government policies and different agent behaviors on the climate, right? So what they called it the shared social economic pathways. So in this graph here, you see that there's like different scenarios, and for each scenario, you can see how much warmer the world will get, right? And so you can see for the blue lines, the world warms up about 1 to 1.5 degrees centigrade. But then for the red lines, the world gets a lot more warm, right? So even the red lines is kind of like, America does not invest in clean energy. It just keeps on burning oil and gas, right? And what's important here is that the IPCC, which is like this big global consortium of scientists, basically, they're like the leading authority in climate science. They said it is really important to understand how governments and countries behave. Their behavior and their policies are going to have a significant influence on what happens with climate. But what is really a big sort of a problem with their analysis is that, again, it's very limited, right? Like, they have no probabilities that they assign to any of these scenarios, right? Like, there's no likelihood of any of these things that they can really compute. Like, there's a lot of questions like, how do negotiation protocols and partial information change the outcomes, right? And what kind of agreements actually make people cooperate? And in particular, like, even if you have an agreement, why would people actually like keep their promise? Like, this is really one of the biggest issues in international climate negotiations that, for instance, in the Paris Agreement, countries promised to invest in green energy, but then, years later, they actually didn't really do that, right? So that's a big issue. Yeah. So what do we what do we want to like then address? Well, from a sort of machine learning perspective, this cooperation problem is very hard because it's in fact a decentralized decision-making problem, meaning that every country here can be seen as this RL agent. They have some climate and economic objectives, right? And then you can say, well, okay, all these countries can negotiate with each other, but there's no central planner or some oversight, like a police agent that's going to enforce actions, right, or enforce agreements. So agreements are non-binding, right? So and there's a bunch of other problems, right? Like there's a lot of uncertainty, like so and people might not agree on the projections about the climate in the world, and so like all of these things together mean that from a machine learning and game theory point of view, this cooperation problem is super hard. Okay. So I talk a lot about negotiations, right? And in this competition, we're asking people to design this negotiation game. So here's just like a very simple example of how that could go, right? So imagine like America or the United States is talking to, I have to look at this country. I think this is Libya or yeah, well, okay. Let's call it some country in Africa. Okay. I apologize. I should have looked up which country I was marking here. Anyway. But bilateral climate negotiation could go something like this, right? So for instance, like, the US proposes to this African country, I'll lower tariffs by 10%. So that trade tariffs, right? It's like, the cost of buying stuff from the US if you mitigate 5% more. And so you can think about this 5% as you need to shut down 5% of your dirty factories, okay? You need to burn 5% less gas in your country. And then a country too could say, no, I don't want to do that. But instead, my counter proposal is I'll mitigate 3% more if you lower tariffs by 50%. Okay. I'm going to do less for more benefit from you. Okay. And then maybe the United States says, sure, okay, I'll accept, right? And then there's some agreement. So during this negotiation process, right, as the designer, you can say, well, these two countries are going to talk to each other. They're going to talk about this particular contract. And what these RL agents then have to decide on is what value goes into these like placeholders, right? 10%, 15%, or and so on, right? And then you can imagine that this ultimately leads to some outcome in the simulation. Okay, so let me skip these two. So how do we like then approach this? So we built a simulation as an organization, and in this simulation, we call it RICE-N. We basically have like a number of fictitious regions, and we are doing this because of political sensitivity. But in the simulation, we're simulating the climate and the economy and the feedback mechanisms between the two, right? And so this is based on the so-called RICE model, which is a recognized model that was developed by a Nobel laureate in economics, William Nordhaus. Okay, and so in the simulation, we have things like if you produce this much CO2, right, then the world will get this much warmer, and it will become more expensive for you to produce more things and so on. But then what we added on top of that is support for reinforcement learning, support for negotiations, international trade, right? And then we also calibrated all the structural parameters of the simulation to real world data. So what's a structural parameter? It says, for instance, if you have this level of technology, like you have a factory that's very old, and this is how much CO2 you're pumping into the atmosphere, right? So that's like an example. Okay, so yeah, this is like a little flow diagram. As I said, this is just like sort of again repeating sort of what I said before. We have this climate, economic, and trade dynamics. So there's a bunch of mathematical equations that model how the climate and the economy are evolving over time. But then there's also this negotiation part on top, where the agreements that these agents can reach with each other then are an input to the climate economic dynamics. Because if you agree to mitigate by this much, meaning like you're committing to emitting less CO2, right? Then that's going to impact the climate and the economy. And just to give you a sense for like the equations, like I don't have enough time to go through all of these equations, but essentially there are a bunch of discrete partial differential equations where, for instance, like, you can look at the temperature, right? And the temperature depends on the temperature from the previous time step, but it also depends on the amount of carbon in the atmosphere. So that amount of carbon is M, right? So like the idea is that, as you put more CO2 in the atmosphere, things will get warmer. And then how much carbon you emit into the atmosphere, so that's the second equation, also depends on the level of productivity. That's this variable Y, right? So the idea is that the more factories you have, right, the more CO2 you're going to emit, and then things will get warmer, right? And so like all these equations here are describing some part of this interaction between economic productivity and temperatures in the world. And there are also things like how much people are in their world, what's your level of technology, how much do you produce, like how carbon intense is your production. And like, it's not super easy, also, but that's not super hard, right? So like it's easy enough that you can put this in NumPy and Numba, and it will run decently fast. Okay. So the interesting thing here is that if you go look at that bilateral negotiation protocol that I showed you before, you can actually see that it actually has a substantial impact on the outcomes in the simulation. So if you, for instance, look at the top left plot here, you can look at how much warmer things get in the simulation, right? So the time axis here, the simulation starts in 2019 and then runs for 100 years at 2119, right? And then you can see in light blue, there's like how much warmer the world gets under the default calibration without negotiation. And you can see that the world gets about 4.5 degrees centigrade warmer, okay? Which is quite warm. But you can see that it roughly corresponds to one of these shared social economic pathway scenarios that I showed you in the beginning that were in an IPCC report, okay? But then you see that once you turn on this bilateral negotiation, and these agents can then start to talk to each other and agree with each other on certain mitigation rates and so on, you can see that the world actually only becomes about 2 degrees centigrade warmer. That's pretty good, 50% reduction, okay? So if you look at the global carbon emissions, you can see the similar picture, right? So one of the main reasons the world doesn't get as warm is because the amount of CO2 that is emitted is actually substantially lower when you have negotiations, right? And the other plots tell you a similar story. Now, the reason that this is not like, okay, well, didn't we actually kind of solve the problem already here, right? Is that obviously this is like a training time result, first of all, right? And this results not necessarily robust at test time, right? So, but this is just like us training the RL agents and showing that yes, negotiations have an impact, but the policies that you get might not necessarily be realistic nor robust, right? And so that's, it's not enough basically to convince people that you should just use this bilateral negotiation and we can all go home and climate change is solved, right? That's unfortunately not true yet. Okay, so as I said, this is a competition so far. And so we had like 3 evaluation tracks where in the first track, we just asked people to submit these curves like the ones that I just showed you. And then we're just going to compare teams to see where they are in the Pareto frontier, basically, when you look at the trade-offs that every team can achieve between the climate and economic performance. In the second track, we asked people, okay, so you have this solution, a bilateral negotiation or some other negotiation protocol, but you should also think about the social aspects and the legal aspects. So is what you propose actually legal and practical? Is there some ethical risk on this, right? Like, why would real politicians accept such a solution to negotiate with each other, right? And then the third track, we are giving people just like carte blanche to propose how the simulation should be improved. Like, maybe it's not completely realistic. That's probably not realistic, right? But how should we make it more realistic? And so one of the things that I found pretty fun is we basically assembled this jury of people. You can see some of their pictures on the right. And really, these people are not just computer scientists, but they also work in climate science, political science, law, economics. And so what we tried is to get a group of people in the jury who are going to look at these submissions that people are going to hopefully submit to us, and really like look at this at the solutions from a very multidisciplinary point of view, right? Because this whole this area of research, right, it's not just come up with better algorithms, but it's also really thinking about like how can you actually use these policies in the real world? Can you really explain the simulation? Can you really think about robustness, both from like a machine learning point of view, but also from like a sort of practical political point of view, right? And that requires a lot more feedback from people who are not machine learning researchers. So the first phase is actually almost done. So you can still compete if you want, but the deadline for submission is like March 31st. And we're going to have a workshop day on April 26th. So it's about 2 months from now. But I sort of like the thinking right now is that this competition is just the first step. And really like what we want to do is after that first step, we want to think bigger and perhaps make a big collaborative research project out of this to basically take this further. And I should mention that one of the objectives here is that once we have these solutions and this analysis, we do want to actually take our results to a paper, and submit it to Nature Climate Change, for instance, but also write a document that we're going to give to politicians. So we've been talking to the OECD, which is like this global policy think tank and organization that's really well connected internationally. And so there's an interest from them to help us take these scientific results and then present them to international governments and politicians and so on. Yeah, so that's pretty exciting, and I really hope that we'll have a good group of people, get them together to go work on this. Yeah, so that was, I think I went over time bar a lot, but that was it. So thanks for listening. And if you want to know more, there's some links here. And yeah, definitely check out this climate change competition. It'd be very cool if some people from Weekend want to work on that too.
Yeah, it's very interesting talk. Yeah, there is a question in the chat box.
Oh, okay. Yeah, let's look at that.
From Adam.
The text there.
Right, at what level?
Yeah, can you read it first and then?
Yeah. So Adam asks, at what level do you introduce heterogeneity into the agents? Is each a separately trained neural network, or can you train a single model with some individual agent-specific input values? Yeah, it's the latter. So one agent model, but with different observations, different private skill levels that are specific to the different agents. Yeah. So the second one.
Yeah. Okay. So hi Adam, is this answer sent by you?
Hello?
No, it's changing.
I'm sorry, I also had another question. Can you hear me okay?
I cannot. Yeah, right now we can hear you. Right now. Yeah, sure. If you have further question, you can email Stephan. Then let's conclude today's talk. Thank you very much. There's a following questions.
Oh, yeah. So Adam asks, do the agents drop out of the simulation under any conditions? Do they go bankrupt, starve to death, etc.? No. Well, they can go bankrupt, but it doesn't mean they can't do anything. They don't die. At least, yeah, not in the income tax simulation. They don't die. 10 years, they're happy. But I'll say that we are working on some, this is a project that's not public yet, but in that project, there is going to be some form of life and death. Yeah.
May I ask a small technical question?
Yeah.
Do we have any association for the data distribution of tested and trained about AI model?
Do we have any measure?
Because in the traditional machine learning, we usually assume the training data and test data operate the same distribution.
Mhm.
So in AI economic model, we have the same thing.
Yeah, I mean, there's different levels. Yeah. So in economics, you can also think about just like a supervised learning setup, right? Like training and test distributions.
I mean,
Yeah.
according to the free lunch theorem, if we do not have any assumption for the data, all of them will have the same good or same worse result. So I think the distribution assumption is pretty critical to whether the AI economic model is really learnable.
Yeah. I mean, if I understand the question correctly, yeah, like so in this paper about mermaid, right? Like actually, like I kind of skipped over this, but here, like in this graph here, one of the training test distribution or difference in the distribution comes from the different agent models, right? So if you have what happens a lot is that in simulations and economic models, you have rational economic agents. But then at test time, you have irrational economic agents, meaning that like their policy model is very different. Their objectives are very different. The utility function might be different, right? And that causes a big shift in the distribution basically between training and testing. So that's like a very important one in economics. Oh, that's not a question. All right. Adam asks, have you been able to figure out why AI learns to tax very low endowed brackets at the highest rates? That seems counterintuitive. Yeah. I want to be careful because, of course, I can give you an explanation, which is a bit of a post hoc explanation, right? But one way to think about it is that in a very simplistic way, right? If you have very high taxes, why would an AI policy have, let's say, so why does an AI policy use low taxes rates? Well, that makes it more attractive for agents to make money in that income bracket, right? Now, if you have very high taxes, then you'd think, yeah, well, but then it's like, it's not very like attractive to work in that bracket, right? So what you want is like, if you're the government, right, you actually want high taxes because then you get a lot of money, but you know that people are also going to work less, right? So what you do is like, you basically tax a lot at the low levels, as long as you basically can make the tax rates lower at a higher income, because you basically like are punishing them for working for the amount of money in the lower tax brackets, but you make it very attractive to work more so they can actually reach the higher tax brackets, right? And that balance basically is something that you can try to optimize, right? Such that like the government like maximizes its sort of tax income. And then at the top end, what you can say is that, yeah, like, you know, at the top end, these people are so rich, right? That like, they don't really feel the difference anymore between higher or lower tax rate for the amount of money they make in the highest bracket. So then the government can get away with you know, having a high tax rate. It's not the highest, but it's also not very low. And again, this is like sort of like a balancing act, right? So I think that those two explanations partially explain why like you have this weird up and down structure to the tax policy. But yeah, I mean, I'm not going to claim that that's like the best explanation. Hope that made sense.
Okay, all right. Thanks again for Stephan's great talk. Yeah, if you have further questions, please ask him through email. Thanks again for listening. Then this is the end of today's seminar. Bye-bye.
Cool. Yeah, thanks for listening, guys.
Yeah.
Have a good day.